Welcome back to the channel. In this video, we are going to build and simulate a complete grid-connected photovoltaic system in MATLAB and Simulink using a multi-string inverter architecture. This type of system is widely used in real-world solar installations because it allows multiple photovoltaic strings to operate independently, even when they are exposed to different irradiance or temperature conditions. Instead of forcing all the panels to share a single operating point, each string gets its own DC to DC boost converter and its own maximum power point tracking loop. All of these converters then feed a shared DC link, which powers a single grid-connected inverter. Here is what we will cover in this video. First, we will look at the overall structure of the model, including the two photovoltaic generators, the two boost converters, and the grid-side inverter. Second, we will explain how the Perturb and Observe algorithm is used to track the maximum power point of each photovoltaic generator by continuously adjusting the duty cycle of its boost converter. Third, we will look at how voltage-oriented control is used on the inverter side to regulate the DC link voltage and inject clean, grid-synchronized current. And finally, we will run the simulation under standard test conditions and analyze the results together. By the end of this video, you will have a clear understanding of how a complete photovoltaic to grid power conversion chain works, from the solar panels all the way to the utility grid, and how each control loop contributes to keeping the system stable and efficient. Let's get started. In this section, we will study the photovoltaic generator, or PVG, which is the heart of every solar energy system. The purpose of the PV generator is to convert solar radiation into electrical energy. In Simulink, the PV generator is modeled mathematically using the equivalent electrical circuit of a solar cell. This model computes the output current based on three important inputs: solar irradiance, cell temperature, and the terminal voltage of the PV array. Let us see how this model works internally. Looking at the subsystem, we can see that it receives three inputs. The first input is the PV voltage, denoted by V. The second input is the solar irradiance, denoted by G or W, measured in watts per square meter. The third input is the cell temperature T, measured in Kelvin. These three quantities completely determine the operating condition of the photovoltaic module. Before studying the MATLAB functions, let us remember the electrical equivalent circuit of a solar cell. A practical solar cell consists of a current source representing the photocurrent generated by sunlight, a diode representing the PN junction, a series resistance, and, sometimes, a shunt resistance. The output current of the PV cell is calculated from the difference between the generated photocurrent and the diode current. Mathematically, the output current equals the photocurrent minus the diode current. Therefore, I equals if minus ID. This simple equation is exactly what we observe inside the Simulink subsystem. Let us begin with the upper MATLAB function block. Its job is to calculate the photocurrent, denoted by if. This current is generated directly by sunlight. The function receives two inputs. The first input is the temperature. The second input is the solar irradiance. Inside the function, several constants are defined. The reference temperature is 298 Kelvin, which corresponds to 25 degrees Celsius. The temperature coefficient is equal to 0.0022 amperes per Kelvin. The short-circuit current under standard test conditions is 3.87 amperes. The scale factor converts irradiance from watts per square meter into a normalized quantity. Finally, the parameter NP1 equals 6, meaning that 6 PV strings are connected in parallel. Since parallel strings carry current together, the total photocurrent will be multiplied by 6. The first calculation determines the effect of temperature. It computes the difference between the actual temperature and the reference temperature. This difference is multiplied by the temperature coefficient. If the temperature increases, the photocurrent increases slightly. If the temperature decreases, the photocurrent decreases slightly. Next, the function computes the irradiance contribution. The short-circuit current is multiplied by the irradiance level. As expected, increasing solar irradiance produces more current. Finally, the photocurrent is obtained by adding the temperature contribution and the irradiance contribution. Since 6 identical strings are connected in parallel, the total current is multiplied by 6. At standard test conditions, where the irradiance is 1000 watts per square meter and the temperature is 25 degrees Celsius, the photocurrent becomes approximately 23.2 amperes. This value represents the maximum current produced by the entire PV array under standard conditions. The second MATLAB function block computes the diode current. The diode represents the physical PN junction inside every photovoltaic cell. Unlike the photocurrent, the diode current opposes the flow of current generated by sunlight. This function receives 3 quantities: temperature, output current, and output voltage. Using these quantities, it calculates the current flowing through the diode. The first step is to calculate the reverse saturation current, usually denoted by I0. This current is extremely small. However, it is one of the most important parameters in photovoltaic modeling because it determines the exponential behavior of the diode. The function uses several physical constants: the electron charge, the Boltzmann constant, the diode ideality factor, the open circuit voltage, the semiconductor bandgap energy, and the number of series-connected cells. This equation computes the saturation current at the reference temperature. Since semiconductor devices are highly sensitive to temperature, the saturation current must be corrected whenever the temperature changes. As temperature increases, the saturation current increases exponentially. This explains why the PV voltage decreases on hot days. After computing the saturation current, the model calculates the diode current using the Shockley diode equation. The exponential term is responsible for the nonlinear behavior of photovoltaic cells. At low voltages, the diode current is almost zero. As the voltage increases, the diode current rises exponentially. Finally, the PV output current is calculated by subtracting the diode current from the photocurrent. When sunlight increases, the photocurrent increases, producing more electrical current. On the other hand, increasing the terminal voltage causes the diode current to rise exponentially, reducing the output current. This interaction between the photocurrent and the diode current creates the well-known nonlinear current voltage characteristic of photovoltaic panels. Now that we understand how the PV generator produces its voltage and current, the next step is to learn how the system extracts the maximum available power from the PV array. In the next section, we will study the Perturb and Observe, or P&O, maximum power point tracking algorithm, which continuously adjusts the operating point of the PV generator to ensure that it delivers its maximum possible power under changing weather conditions. Now that we understand how the photovoltaic generator produces electrical power, the next question is, how can we make sure the PV array always operates at its maximum power point? The answer is by using a maximum power point tracking algorithm, commonly known as MPPT. In this model, the MPPT technique used is the Perturb and Observe, or P&O, algorithm. The purpose of this algorithm is to continuously adjust the operating voltage of the PV array so that it always extracts the maximum available power, even when the irradiance or temperature changes. The MATLAB function block receives 2 inputs from the photovoltaic generator. The first input is the PV current, denoted by I. The second input is the PV voltage, denoted by V. Using these 2 measurements, the algorithm calculates the instantaneous power produced by the PV array. The output of the function is the new reference voltage, called VPV. This reference voltage will later be used by the PWM controller to regulate the boost converter. At the beginning of the program, we notice the keyword persistent. Persistent variables are special variables that preserve their values between consecutive function calls. This is extremely important because the P&O algorithm must compare the current measurements with the previous measurements. Without memory, the controller would not know whether the power has increased or decreased. The variables stored are P previous, which stores the previous power, VZ1 and VZ2, which store the previous voltage samples, VPV previous, which stores the previous reference voltage. During the first execution, these variables are initialized to 0. The next line defines the perturbation step size. This value determines how much the operating voltage changes during each iteration. A small step size produces smoother tracking with less oscillation around the maximum power point. However, if the step is too small, the tracking speed becomes slower. On the other hand, a larger step allows faster convergence, but causes larger oscillations and greater power loss. Therefore, selecting the perturbation step is always a compromise between speed and accuracy. The instantaneous photovoltaic power is calculated as power equals current multiplied by voltage. This is simply the electrical power equation. Power equals voltage multiplied by current. This value represents the amount of electrical power currently generated by the PV array. Next, the controller calculates the change in power. This is the current power minus the previous power. This tells us whether the last perturbation increased or decreased the output power. If the change in power is positive, the operating point moved toward the maximum power point. If the change in power is negative, the operating point moved away from the maximum power point. Next, the voltage change is calculated as the voltage 1 step ago minus the voltage 2 steps ago. This quantity indicates the direction of the previous voltage perturbation. A positive value means the voltage was increased. A negative value means the voltage was decreased. Now comes the heart of the perturb and observe algorithm. First, the controller determines whether the power increased. Next, it determines whether the voltage increased. Then it compares both directions using the exclusive OR operation. The exclusive OR operator returns true only when the two logical values are different. This single operation allows the controller to decide whether it should continue in the same direction or reverse the perturbation direction. The controller follows 4 simple rules. If the voltage increased and the power increased, it continues increasing the voltage. If the voltage increased but the power decreased, it reverses direction and decreases the voltage. If the voltage decreased and the power increased, it continues decreasing the voltage. If the voltage decreased and the power also decreased, it reverses direction and increases the voltage. This is exactly the classical perturb and observe algorithm. The voltage step is then generated. This line simply selects either a positive perturbation or a negative perturbation. If the previous perturbation improved the power output, the voltage continues changing in the same direction. Otherwise, the controller changes direction. The next step applies a gate to that perturbation. This is an important improvement. If the measured power does not change, there is no need to modify the reference voltage. Therefore, the perturbation is disabled whenever the power difference is exactly 0. This reduces unnecessary oscillations around the maximum power point. The new reference voltage is then computed. The controller starts from the previous reference voltage and either increases or decreases it by 1 perturbation step. This updated voltage becomes the new operating point of the PV array. Finally, the controller stores the latest values for the next sampling period. The voltage 2 steps ago is updated to the voltage 1 step ago. The voltage 1 step ago is updated to the present voltage. The previous power is updated to the current power. And the previous reference voltage is updated to the newly computed reference voltage. This continuous updating allows the controller to compare the present operating condition with the previous one and make the next decision. The complete operation of the perturb and observe algorithm can be summarized in 5 simple steps. First, measure the PV voltage and current. Second, calculate the output power. Third, compare the current power with the previous power. Fourth, decide whether to increase or decrease the reference voltage. Fifth, repeat the process continuously until the operating point converges to the maximum power point. At this stage, the MPPT algorithm has determined the optimum reference voltage for the photovoltaic array. However, the PV array cannot change its voltage directly. Instead, this reference voltage is sent to the PWM controller. The PWM controller compares the measured PV voltage with the desired reference voltage and generates the switching pulses required to control the boost converter. In the next section, We will see how the PI controller and the PWM generator work together to regulate the boost converter and force the PV array to operate exactly at the voltage selected by the MPPT algorithm. The boost converter is one of the most important components in a photovoltaic energy conversion system. It is a DC to DC converter whose primary purpose is to increase the relatively low voltage produced by the photovoltaic array into a higher DC voltage suitable for the inverter and the DC link. Besides increasing the voltage, the boost converter also provides the mechanism through which the MPPT algorithm controls the operating point of the PV array. Let's look at the main components. The boost converter consists of 4 main parts: an inductor, a power switch implemented using an IGBT, a diode, and an output capacitor. Each component plays a specific role in the energy conversion process. The inductor is responsible for storing energy in the form of a magnetic field. Whenever current flows through the inductor, magnetic energy is accumulated. This stored energy is later transferred to the output, allowing the converter to produce an output voltage greater than the input voltage. The IGBT acts as a high-speed electronic switch. It is controlled by the PWM signal generated in the previous subsystem. Depending on the PWM command, the IGBT repeatedly turns on and off thousands of times per second. The diode ensures that energy flows only toward the output. It blocks any reverse current from flowing back into the photovoltaic array. The output capacitor stores electrical energy and smooths the output voltage. Without this capacitor, the output voltage would contain significant ripple due to the switching operation. Now let's look at the operating principle. The operation of the boost converter can be divided into 2 modes. In the first mode, the switch is on. When the PWM signal turns the IGBT on, the diode becomes reverse biased. During this interval, the photovoltaic source supplies current directly to the inductor. The inductor stores energy in its magnetic field, while the output capacitor supplies the load. The inductor voltage is approximately equal to the PV voltage, and the inductor current increases linearly. In the second mode, the switch is off. When the PWM signal turns the IGBT off, the magnetic field inside the inductor collapses. According to Faraday's law, the inductor opposes the sudden decrease in current by generating a voltage of opposite polarity. This induced voltage is added to the PV voltage. As a result, the diode becomes forward biased, and the stored energy is transferred to the output capacitor and the load. Next, let's talk about voltage gain. Under ideal continuous conduction mode, the output voltage equals the PV voltage divided by the quantity 1 minus D, where D is the duty cycle. This equation clearly shows that increasing the duty cycle increases the output voltage. For example, if the duty cycle is 0.5, the output voltage becomes 2 times the PV voltage. And if the duty cycle is 0.75, the output voltage becomes 4 times the PV voltage. This illustrates why controlling the duty cycle is so powerful. Finally, let's connect this back to the MPPT. The MPPT algorithm does not directly change the photovoltaic voltage. Instead, it changes the reference voltage. The PI controller adjusts the duty cycle. The duty cycle controls the boost converter. Finally, the boost converter changes the operating voltage of the photovoltaic array. In this way, the MPPT algorithm continuously drives the PV array toward its maximum power point, while simultaneously supplying a stable high-voltage DC output for the grid-connected inverter. This part of the model represents the grid-connected inverter stage, controlled using voltage-oriented control, often called VOC. At the center of this section is a 3-phase inverter, built from IGBT switches. It converts the DC voltage coming from the boost converters into a 3-phase alternating current waveform. This inverter is switched using the PWM pulses generated by the VOC controller. The inverter output passes through 3 filter inductors, labeled L1, L2, and L3. These inductors smooth the switched waveform, removing high-frequency ripple and producing a cleaner sinusoidal current before it reaches the grid. After the filter inductors, a measurement block captures the three-phase voltage and current, labeled VABC and IABC. These measured values are essential feedback signals for the control system. The inverter is then connected to three controlled voltage sources, which represent the grid. Together, these three sources form a balanced three-phase AC supply that the inverter must synchronize with and inject power into. Below the power stage, a gray subsystem gathers three key signals: the grid current, labeled I grid, the grid voltage, labeled VG, and the DC link voltage, labeled VDC. These three signals are sent to the VOC control system, which decides how the inverter should behave at every instant. Now let's look at how the VOC controller itself works, shown in the lower part of the diagram. The control system begins with the DC voltage regulation loop. The measured DC voltage is compared with a fixed reference value of 400 volts. The difference between them passes through a PI controller. The output of this controller becomes the reference for the direct axis current, labeled ID reference. This is the core idea behind voltage-oriented control. By regulating the DC bus voltage, the controller indirectly determines how much active power the inverter should exchange with the grid. At the same time, the grid voltage is transformed from the three-phase ABC frame into the rotating DQ0 frame. This transformation uses the frequency and phase angle extracted from the grid voltage itself, acting as a virtual phase locked loop. This step allows the controller to represent grid quantities as steady values instead of sinusoidal waveforms, which makes accurate regulation possible. The measured grid current is transformed into the same DQ0 frame, producing the direct axis current and the quadrature axis current, labeled ID and IQ. Two current control loops then operate in parallel. The direct axis current is compared with its reference and processed by a PI controller. The quadrature axis current is compared with a reference of 0 and processed by a separate PI controller. Keeping the quadrature current reference at 0 ensures that the inverter operates at unity power factor, exchanging only active power with the grid. Cross-coupling terms, based on the grid angular frequency multiplied by the filter inductance, are added to each loop. These decoupling terms compensate for the natural interaction between the direct and quadrature axes, allowing each current loop to be controlled independently. The outputs of the two current controllers produce the direct axis and quadrature axis voltage references, labeled VD and VQ. These are then transformed back from the DQ0 frame into the three-phase ABC frame, producing the reference voltage waveform the inverter must generate. This reference voltage passes through a rate limiter and a one-sample delay, which is standard practice in discrete simulation to avoid algebraic loops between the controller and the power stage. Finally, this reference becomes the URF signal, which feeds the PWM generator to produce the switching pulses that drive the inverter. In summary, this section takes the DC link voltage, the grid voltage, and the grid current, and uses them to compute exactly how the inverter should switch, so that the DC bus voltage stays regulated at 400 volts while the inverter injects clean, grid-synchronized current at unity power factor. Now, let's analyze the simulation results of the grid-connected photovoltaic system operating under standard test conditions. In this simulation, the solar irradiance is maintained at 1000 watts per square meter, while the cell temperature is fixed at 25 degrees Celsius, or 298 Kelvin. Since both photovoltaic generators receive the same irradiance and temperature, they produce identical electrical power. As a result, both boost converters operate under the same conditions and deliver equal power to the common DC link. Let's begin with Scope 1, shown on the left. The first graph represents the three-phase output voltages generated by the inverter. We can clearly observe three balanced sinusoidal voltages that are displaced by 120 degrees from each other. This confirms that the voltage-oriented control, or VOC, is successfully generating a balanced three-phase voltage system. The smooth sinusoidal waveforms also indicate that the inverter is operating in a stable condition. The second graph shows the three-phase output currents. Similar to the voltages, the currents are balanced and separated by 120 electrical degrees. Because the system operates under constant irradiance, the output currents remain constant in amplitude throughout the simulation. This indicates that the photovoltaic system continuously delivers nearly constant active power to the electrical grid. The third graph represents the DC link voltage. We can see that the DC link voltage is regulated around 415 volts with only a very small ripple. This is exactly the expected behavior. The DC link capacitor stores energy and smooths the voltage, while the voltage-oriented controller continuously regulates the power exchanged between the photovoltaic array and the grid. The small ripple observed in the waveform is mainly caused by the high-frequency switching of the inverter and is considered normal in practical power electronic converters. Overall, the nearly constant DC link voltage demonstrates that the controller is maintaining a stable operating point. Now, let's examine Scope 2, shown on the right. The upper graph displays the three-phase grid currents. Again, we observe three balanced sinusoidal currents with equal amplitudes and a phase displacement of 120 degrees. The absence of distortion indicates that the inverter injects clean electrical current into the utility grid. The lower graph shows the three-phase grid voltages. As expected, the voltages are balanced sinusoidal waveforms representing the electrical utility. The inverter continuously synchronizes its operation with these grid voltages using the voltage-oriented control strategy. One important observation is that the inverter current follows the grid voltage. This synchronization is essential for grid-connected photovoltaic systems because electrical power can only be transferred efficiently when both voltage and current are synchronized in frequency and phase. Since the Q-axis current reference is set to 0 in the voltage-oriented control algorithm, the inverter injects almost purely active power into the grid. Consequently, the system operates with a power factor close to unity, minimizing reactive power exchange. The simulation results confirm that all parts of the photovoltaic system operate correctly. The Perturb and Observe MPPT algorithm continuously tracks the maximum power point of each photovoltaic generator. The boost converters regulate the operating voltage of the PV arrays and increase the DC voltage supplied to the DC link. The DC link capacitor maintains a nearly constant DC voltage despite the inverter switching action. Finally, the voltage-oriented controller generates balanced switching signals for the inverter, allowing clean sinusoidal currents to be injected into the utility grid. Now, let's look at the simulation results under variable irradiance conditions. Unlike the previous test at standard test conditions, the irradiance here is no longer constant. Instead, it is defined using the signal builder block, shown in the bottom right corner of the model. This block generates a stepped irradiance profile over time. The irradiance starts at around 1,000 watts per square meter, then drops sharply to around 600 watts per square meter, and finally rises again to settle at around 800 watts per square meter. This kind of step profile is commonly used to test how quickly and how smoothly the maximum power point tracking algorithm can react to sudden changes in solar irradiance, similar to the effect of passing clouds. Let's look at how the system responds to these changes. In the bottom left scope, the DC link voltage is displayed. Under normal operation, this voltage stays regulated close to its reference value of around 412 volts. You can see some ripple and small transients in the waveform, which is expected due to the switching action of the converters and the sudden changes in irradiance. Even so, the DC link voltage remains tightly regulated around its target value, showing that the voltage-oriented control loop is successfully keeping the DC bus stable, regardless of how much power the photovoltaic generators are producing at any given moment. In the top left and top right scopes, we can see the three-phase voltage and current waveforms measured at two different points in the system. These waveforms remain smooth, balanced, and sinusoidal throughout the simulation. This confirms that even as the irradiance changes and the power delivered by the photovoltaic generators varies, the inverter continues to inject clean three-phase current into the grid, synchronized with the grid voltage. Overall, these results demonstrate that the control system performs well under realistic, time-varying irradiance conditions. The Perturb and Observe algorithm continues to track the maximum power point of each photovoltaic string as the irradiance steps up and down. At the same time, the voltage-oriented control loop keeps the DC link voltage stable and ensures that the power extracted from the photovoltaic arrays is properly delivered to the grid, with minimal disturbance to the quality of the injected current. This confirms that the multi-string grid-connected photovoltaic system is not only effective under ideal, constant irradiance conditions, but also robust and responsive when the solar input changes rapidly and unpredictably, which is exactly the kind of behavior expected from a real photovoltaic installation operating under natural, variable sunlight. And that brings us to the end of this tutorial. Throughout this video, we've built and explored a complete MATLAB/Simulink model of a grid-connected photovoltaic system based on a multi-string inverter architecture. We began by understanding the mathematical model of the photovoltaic generator, then examined how the Perturb and Observe MPPT algorithm continuously tracks the maximum power point of each PV string. Next, we studied the operation of the DC-DC boost converters, followed by the PWM generation process, and finally the voltage-oriented control strategy that regulates the grid-side inverter. One of the key advantages of this multi-string configuration is that each photovoltaic generator operates independently. Each PV string has its own boost converter and MPPT controller, allowing it to extract the maximum available power even if different strings experience different environmental conditions, such as unequal irradiance or temperature. On the grid side, the voltage-oriented controller maintains a stable DC link voltage, while ensuring that the inverter injects balanced, sinusoidal currents synchronized with the utility grid. This enables efficient active power transfer with a power factor close to unity and excellent power quality. The simulation results under standard test conditions confirm the effectiveness of the proposed system. The MPPT controllers successfully converge to the maximum power point. The DC link voltage remains well regulated, and the inverter delivers clean three-phase power to the electrical grid with stable operation. Overall, this demonstrates that combining Perturb and Observe MPPT with voltage-oriented control provides a reliable, efficient, and practical solution for grid-connected multi-string photovoltaic systems. I hope this tutorial has helped you better understand not only how this Simulink model is constructed, but also the theory behind each subsystem and how all the components work together as a complete renewable energy conversion system. If you found this video helpful, please give it a thumbs up, subscribe to the channel, and turn on the notification bell so you don't miss future tutorials on power electronics, renewable energy systems, MATLAB, and Simulink. If you have any questions or topics you'd like me to cover, feel free to leave them in the comments below. I always enjoy hearing your feedback and suggestions. Thank you very much for watching. I truly appreciate your time and support. Until next time, keep learning, keep experimenting, and keep building. See you in the next video.